where we shall be looking at the proposed memorandum for the Physical Sciences Paper 1 for September 2025. Okay, so this paper is a 3-hour paper with 150 marks. We have 16 pages and we have a total of 10 questions that we have to work with, and we need to answer all of them. Okay. Let's start with the MCQ, which is question number 1. And they're telling us that a mass hangs from a vertical string that is attached to the ceiling. Okay. Which of the following Newton's third law pair for the weight of the mass? Okay, in other words, which pair goes with the weight of the mass? So A, we are being told that the force from the ceiling acting on the mass. Nope. The tension, the string that is acting on the mass. Not really. The gravitational force exerted by the mass on the earth. Okay, gravitational force exerted by the earth on the mass. Okay, so I'll go with C. Okay, because it's more like definition of what mass is. Then 1.2, a block is at rest on a rough surface. The surface is at an angle theta to the horizontal. The block remains at rest as the angle slowly increases. Which of the following best describes the magnitude of the static friction force of the rough surface on the block and the normal force as theta changes? So we know that when the angle is increased, the static frictional force must decrease. In other words, the ease with which this block will easily slide is very high, okay? So we're going to look for options that have increase. That is option, whoa. How will it increase? It will actually decrease. I mean, it will easily slide, which means we're looking at the decrease option, which is C. Okay, but if it decreases, then what's going to happen to the normal force? We know that the normal force will be the FG perpendicular, which is the normal force. We said it's mg cos of theta. Okay, so as this theta increases, maybe from 0 up to 90, the overall value becomes smaller. Okay, so we know that the normal force is going to decrease. So option C becomes the best option there. Then 1.3, if a ball A is thrown vertically upwards with a speed v from the top of the building, and then at the same time, the ball B is thrown vertically downwards with the same speed, both balls which reach the ground at the same time. If we are ignoring the effects of friction, which of the following is true about the speed at which the balls hit the ground? So regardless of how much time one ball takes and the other, and in this case, we could be having some sort of scenario of masses being different, okay? Because we're not being told whether the balls are of the same masses, the same size, or what. They are probably different masses, okay? And if that is the case, they're asking us which one of the following is true. The speed of ball A is greater than ball B. That's not gonna happen because the throwing time was the same when they both went up, and then they are both hitting the ground at the same time. Something is fishy here. The speed of B is greater than that. No, the speed of B is equal to the speed. I'll go with option C. Okay, I'll take option C for 1.3. Then 1.4, they're telling us that two trolleys of masses 3 and 2 are connected to each other and they're moving at some unknown velocity, v. A small explosion between them causes the trolleys to move apart in the opposite directions, and then the trolley of mass 3 moves to the left with v, and then that of 2m moves to the right with 4v. Which of the following statements will be correct? Okay, they want us to get the momentum before and then the kinetic energy after. Okay, so Let's start with the momentum before. So before the impact or before the explosion, this was like one block. Okay, and we know that momentum is mass multiplied by the velocity. So the masses are going to be 5m. Now we are multiplying it by v, which we don't know. Okay, meaning that the initial should be 5mv. So we're looking at option B and option D. Okay. Then when we look at the total kinetic energy after, so meaning that with a 3m body, it will be a half times 3m multiplied by the v squared. Okay. This is going to be like a minus v if I'm taking left to be negative. Plus, this is going to be a half times 2m multiplied by the 4v, but that is going to be squared. Then when I look at this is going to be 3mv squared over 2 plus this 16 times 2, that's going to be like 32 mv squared over 2. When I plus that together, I'm going to get a 35 mv squared over 2. And then I divide by 2, I'll get a 17.5 mv squared. So I'll go with this, which is option B for my case, okay? I'll take that. And as much as directions are different, I'm taking the directions into consideration and I'm ending up with that as the total energy. Okay, 1.5. If a car is moving in a straight line, the velocity of the car decreases with time as shown in the graph below. Which of the following graph best represents the power of the braking system? So what we can see is that this vehicle, this car is decelerating at a constant rate, meaning that the power that is also being applied should also do the same, because we know that power is the same as the force multiplied by the change in velocity. Now, if the velocity is decreasing at a constant rate and velocity is directly proportional to the power, then meaning that the power must also decrease at the same rate. Okay, so that is option D. Then 1.6, a car moves at a constant velocity towards the learner who is standing on the side of the road. The driver hoots as the car moves towards the learner. Which of the following statements will be correct? The speed of sound heard by the learner is higher than the speed of sound emitted by the hooter. No. Okay, there is some bit of truth here. If it's moving towards, the speed of sound heard by the learner is higher. Like, why are they using the word higher, not louder? But no. Let's read. What are they saying? The speed of sound. I mean, speed of sound cannot be heard. So this is out. B, the wavelength of the sound heard by the learner is higher than the wavelength of the sound. What is supposed to be higher is the frequency, not the wavelength. The frequency of the sound heard by the learner is higher than the frequency. So option C will be the best option there. And then 1.7. 1.7, they're telling us two small spheres, each with a net charge of minus Q, exert a force F on each other. One of the charges is now replaced by another that is negative 4Q. If in the process, the distance between the two is doubled, and then they want us to find the force that one exerts on the other after the changes have been implemented. So meaning that F is equal to K Q1 Q2 over R squared, okay? Now, if we are replacing 1 with a negative 4Q, so Q1 negative 4Q, we don't need the negative, just the 4Q. You're dividing by the distance, which has been doubled, so twice that. So by the top, we shall have a 4K Q1 Q2 over 2 squared is going to be a 4 R squared. So this 4 cancels this 4, which takes us back to the original. So A becomes the best option there. And then 1.6, a battery with an EMF E, an internal resistance R, okay, is connected to a switch S and two identical resistors as shown in the sketch below. Then Which of the following statements is correct when the switch is closed? Okay, so the voltmeter reading will be E. Remember, the E is the EMF when an ideal voltmeter is connected across the two. Okay, the voltmeter reading E, so the voltmeter reading is less than E when an ideal voltmeter is connected across the battery. So I think the second one makes a lot of sense, because once you connect a voltmeter across, the reading of the voltmeter must drop. It must be smaller than the original EMF when the switch was open. So I'll go with B as my option there. Then 1.9, which of the energy conversions take place in an AC generator? So regardless of whether it's AC or DC, what is important is a generator. Energy conversion is basically mechanical to electrical. And then 1.10, they're telling us the energy diagram for an element is shown below. The electron transmission A from E2 to E1 corresponds to a green line in the element spectrum. Then transition B is from E0 to E1. It corresponds to which type of light? Okay. Okay, so we know that when an electron moves from a higher energy level to a low energy level, we shall be dealing with emissions, okay? But then if it moves from a low energy level to a higher energy level, we shall be dealing with an absorption. So the correct option here, because we're talking of an element, and then the transmission A from E2 to E1 corresponds to green line in the electron spectrum, and then transition B from E0 corresponds to, so it should be an absorption. Okay, it's going to be an absorption, but is it green light or the red light? Because we can see there is a very big space. So I'm gonna go with the absorption of the red light. Okay, then question number 2. They're telling us that block A has a mass of 5 kgs, and then block B has a mass of 3 kgs. Block A is placed on a rough table with a coefficient of static friction being 0.2. Block A and C are connected via a light inextensible string or rope of a frictionless pulley, and block B is just placed on top of A. Okay, define the term normal force. So we know that normal force, or they told us the system is only just at rest and on point of sliding, okay? So normal force refers to the perpendicular force. Okay, we know that's the perpendicular force that is exerted by a surface, on an object that is in contact, with it, I mean the surface, that must prevent it, okay, preventing it from sinking into the surface. Okay, it's basically that force that will try to hold up the object. Then 2.2, they want us to determine the tension that is within the string. So what we can see is that if there's tension there, then the weight will be down here, meaning that our tension is equal to W for the C. And then tension is going to be the mass of the C times G. So C is a 3 multiplied by 9.8. And that gives me a 29.4 newtons. All right, then 2.3, they want us to draw a free body diagram showing all forces that are acting on A. Now we have 5 marks, so meaning we can have round about 5 forces minimum. So when you look at A, we're going to have the weight of A. We're also going to have the weight of B. Then we're going to have the normal force of A. And then maybe we can even do a combination of the two. Normal force of A and the normal force of that. Then we're going to have the tension there, and then we're going to have the frictional force Fk in that sort of direction. So the weight of A, weight of B, we said frictional force, we're going to have the tension, and then we're going to have the Fn of A, Fn of B. Okay, so something like that for 5 marks. Then they want us to calculate the minimum weight of B needed to prevent A from sliding. So if I write it this side, okay. So we're saying that if we look at A, we say this is the Fk, this is the Fn of A and B. This is the weight of A and B. That's not relevant, but there's tension this side. They want us to get the minimum weight of A. So what must we do in that case? So we know that since the object is just stationary, or since the system is just stationary, and they gave us the frictional force, the static friction coefficient, we know that F net is equal to MA, and then the tension must be equivalent to the Fs, okay, kinetic friction. And in that case, I'm going to use my tension is equal to mu multiplied by the normal force, okay? So the tension we got was a 29,4, is equivalent to the coefficient, which is a 0,2. And then the normal force, remember, normal force is equal to the weight of these two. So I'm going to say the mass of A plus the mass of B multiplied by the 9,8. Okay, so you're going to have a 29,4. What is 9,8 and 0,2? When I punch that into my calculator, what we obtain? What we obtained? So 9,8 multiplied by the 0,2. Well, this gives me a small answer of 1,96. Okay. Into, we know that the mass of A was a 5. So this is going to be a 5 plus the mass of B. Okay, let's divide both sides by 1,96 over 1,96. This cancels that. So 29,4 divided by 1,96, I'm getting a 15 is equal to 5 plus the mass of B. Let's move the 5 that side, meaning that the mass of B is going to be 10 kgs. What was the question asking for? Calculate the minimum weight. So we know that weight is equivalent to mass times the gravitational force. So that's going to be like a 10 multiplied by the 9,8, which gives us 98 newtons. Okay, then 2.4 is done and the whole of question 2. We move on to question number 3. They're telling us that there's a learner that stands on a balcony that is 5 meters above the street or above the ground and throws ball A vertically upwards at a velocity of 5 meters per second. At the same time, there's another learner that throws ball B vertically upwards from the street with an inertia of 8. Ignore the effects of air friction. Then they want us to define what projectile motion is. So we know that projectile motion okay, so we're saying that when you talk about a projectile motion, it's basically the motion on an object with an initial velocity, and the rest of the motion must be entirely under the influence of the acceleration due to gravity. Okay, so we could say that the motion of an object with an initial velocity. Okay, so initial velocity. Okay, and under the influence of the acceleration due to gravity only. Okay, so gravitational force is the only force that is acting on this object. Okay, then 3.2, they want us to calculate the maximum height above the ground that is reached by A. So we know that at the maximum height, our final velocity will be 0. So if we use Vf is equal to V initial plus A delta T. Okay, so if you look at the upward, I'm going to take it to be negative. Okay, meaning that what do we want? We want the maximum, but there's no height here. So we can't use this formula for first equation. Let's use the change in y is equal to V initial delta T. Is this going to make, no, it's also not going to make sense for me because I don't have time. Let me use the third one. Vf squared is equal to Vi squared plus 2A delta y. I think this is perfect. I have the initial, I need the final. We also need the displacement. Good. So what we're going to do, let's do the substitution. So we say the final is going to be a 0. Our initial is 5 plus 2. Our A is now a G, which is a negative 9,8 delta y. Okay, so when I move this negative 9,8 and the 2 to the other side, I'll have something like a 19,6y is equal to 25. Then I'll divide both sides by 19,6. Okay, so 25 divided by 19,6, that gives me a 1,275, which is like 1,28 meters. But then that is the distance from this point up to the 1,28. The question wants the maximum height above the ground. So we need to plus a 5 there so that we get a 6,28 meters. All right, then 3.3, calculate the time at which the two balls will move at the same speed. Now, for the balls to move at the same speed, if I use, okay, the first equation, meaning that I'm looking for my final velocity. So V final is equal to V initial plus A delta T. Okay. And then, so if this is the first body A, then even the one for B should be more or less the same equation. Now, if I look at this, is it going to make sense? Because this is going to be 9,8T, 9,8T. Then I'm going to have something like 8, something like 5, which won't even make sense at all. Let's try the second one, where we know that the distance that traveled could be the same, or they could be at the same point. So if I use Vi delta T plus a half A delta T squared, okay, is it going to make sense? No. Why don't I stick to the first one? Let me stick to the first one, okay, and play around with the directions, because this T squared is going to be something else, because I'm going to still end up with the same thing. So what I can do is, like for body A, I'll take my initial to be 5 minus, okay, and that's going to be something like a 9,8T is equivalent to, now this should be in the opposite direction, because by the time that one reaches the maximum, this one will be somewhere. So negative into 8 minus the 9,8T. If I look at it this way, okay, meaning that I'll have a 5 minus a 9,8T is equal to negative 8 plus a 9,8T. Let's move this let's move that this side. So it's going to be a 5 plus 8 is equal to 9,8T times 2. Okay, let me just put it that way. So 13 is equal to 19.6T. Divide both sides by 19.6, meaning that our T, so we're saying 13 divide by 19.6, which is a 0.66 seconds. What is the question asking for? Okay, calculate the time at which the two balls will move at the same speed. So I'll give that as my answer. Okay, I don't know how people went about that question. Please just let us know on how you answer that. Then 3.4, ball A reached the maximum height after 0.51 seconds. Okay, so I think this kind of aligns with what we got here, that when the other body is coming down, the other one is still going up. Okay, so calculate the velocity at which ball B was moving when A reached the maximum height. So we can use the first equation, VF is equal to VI plus A delta T. We need the final velocities. We have the time. So initially, B was at 8 plus the negative 9.8 times 0.51. Okay, negative because initially it was projected upwards. So 9.8 times 0.51, I'm getting a 3 meters per second. Okay, so that's what I'm getting for 3.4. Then 3.5, they want us to sketch a velocity time graph, the motion of the two balls until they reach the same speed. Clearly indicate, okay. So the time when they reach the same speed. So what I can say is that my body A started from 5. Body B started from 8. So chances are high that this body reached this maximum. They told us at 0.51. Then 8 was having a velocity of 3, which is somewhere here at the same time here. No, that is a lie. Is it gonna make sense? Yeah, I think so. Which means the direction is just more or less the same. Okay, so at this point, or 0.5, that is your 3, somewhere there. Then this point where the velocities are the same, that's gonna be your 0.66. So I would just label them as A, this is B, this is the time in seconds, this is the velocity in meters per second. So something like that would definitely give us the marks that we need. Feel free to even use different colors for A and then for B. Okay, so then we move on. So some people would argue out that it would be something like, let's not go into that politics now. Saying this and then somewhere there. I don't know. So that's your 0.5 and then this is your 0.6. The velocity being the same, but in the opposite directions. Okay, that is also sensible. Makes some bit of sense. Okay, then we move on to question 4. A learner, what is this saying? A learner is tests. Okay, let's say a learner tests the strength of a piece of glass by dropping a steel ball of 5 kg from a height of 3 onto the glass. Velocity time graph below represents the motion of the steel ball from the moment the learner drops the ball until it reaches the ground. Then they want us to define what momentum is. And so one thing we know is that momentum is the product, okay, of mass, the product of the mass of a body and its velocity. Or the product of the mass of a body and the velocity with which the body moves, okay? Then 4.2, calculate the net force exerted by the glass on the steel ball. So we have the velocities here. We have the same, so we know that F net should be equivalent to the change in momentum, the rate at the rate of change in momentum, okay? More like the impulse part. Then we know that we can get the momentum by simply getting the mass multiplied by V final and V initial. The time of reaction is from 0,8 to 1, which is like 0,2 seconds. So let's do the substitutions and see, since they want F net. We're going to say the mass is still 5 into our V final. We're going to take it to be a 1,53 minus the V initial, which is a 7,84 divided by the 0,2. So when I punch that into my calculator, I'm ending up with a 31,55 newtons. Okay, so that is what I'm getting for my net force. All right, then 4.3. Is this an elastic or inelastic collision? Refer to the data in the graph and the relevant principles to explain the answer. So the fact that this is a steel ball, and I believe as soon as this dropped on the glass, probably the glass shatters or breaks, okay? This is going to be an inelastic collision. Okay, so if we are to look at the graph also, we're seeing that when it is dropped, it spends some time, okay? The reaction time is not that much, okay? And then the velocity with which it is leaving or it wants to leave is very small. It's very minimal, which is 1,53, which is a very big drop. So there is a very big loss in energy due to the fact that the energy was transmitted into the broken glass. So the interaction between the glass and the ball. So it's saying it is inelastic because the rebound speed, okay, the rebound speed of 1,53 meters per second is way less than this, the 7,84, the initial one. Okay, which indicates what we call energy loss. Okay, so if you're to use equations, you can look at the kinetic energy. Okay, you calculate the kinetic energy initially and the kinetic energy at this point. You would see that there's a difference before the collision and immediately after the collision. Then 4.4, they're telling us that the glass does not break when a learner drops a soft rubber ball with a similar mass, the same height. Can we explain why? So we know that both balls have the same mass, né? They have the same mass. But the falling, yes, it is also from the same height. So the only difference is that the rubber is more elastic compared to the metal ball, okay? So meaning that the impact, okay, the impact speed of the rubber ball is going to be higher, okay? It's a bit higher or greater than for the metal ball. And then the other thing that we also need to look at is that the glass does not break under the rubber due to the difference within the collision. So the rubber it deals with the elastic collision, unlike the metal ball, which deals with the inelastic. Okay, so an explanation like that, maybe around that area, would give you the 3 marks. Then question number 5. They're telling us that a motor is used to pull a crate of mass 60 kilograms up a 30-meter rough slope. The motor is connected to the crate with a string that is inextensible, that is running over a pulley. The slope is 25 degrees. The crate starts from rest. So the V initial is 0 and reaches a speed of 7,5. V final is 7,5 at the top here. The crate experiences a frictional force of 16,2 newtons. Can you define the term in non-conservative force? So it's a force in which the work done depends on the path taken. The work done depends on the force on the path taken. Then for 7 marks, we must use the work energy theorem to calculate the average power that the motor must provide to catch up in 2 minutes. So one thing we need to know before we even start is that power is given as the work over the change in time, okay? The work done, since we're talking about the motor, which means we're gonna look at the tension. The work done by the tension, then divided by the change in time. Now, let's start with the 60 kg. If we look at the free body, there's going to be tension there. We're gonna have the frictional force. We're gonna have the FG parallel in that sort of direction. So let me start with those three. And then I proceed to look for what my tension force is. And so we know that W net is equal to the change in EK, okay? But my W net is going to be the tension force because the direction is upwards, okay? The tension force minus, why don't I say the work done by the tension plus the work done by the frictional force plus the work done by the gravitational force should be equivalent to the change in EK. So the work done by the tension, I don't know. With the frictional force, we know that it is a 16,2 multiplied by 30. Then I'll multiply this by the cos of 180 because the opposite direction. The FG parallel is given as mg sine of theta. That's just the force. So if we have our mass as 60, okay, multiplied by the 9,8, the sine of 25, this is just the force. Let's multiply it by the distance, which is 30, okay? And then I will multiply it also with the cos of 180 is equivalent to a half, okay, kinetic energy times the mass, which is 60, and then it's gonna be VF squared, which is the 7,5 squared minus 0 squared. Okay, then WT. So when I simplify the 16,2 multiplied by 30 and then the cos of 180, I'm getting negative 486. And then when I look at this, I have 60 times 9,8 multiplied by the sine of 25, okay, and then multiplied by 30. It gives me negative 7454,986. Okay, is equivalent to a half, that is 30, multiplied by 7,5 squared, which gives me 1687,5. Okay, then I need to move all this to that other side, meaning that my tension force is going to be 1687,5 plus 486 plus 7454,986. Why don't I just say 97? All right, so it's going to be a plus 486, so plus 7454.986. I'm getting 9628,49. Okay, let's leave it as 486. So this is the work done, which is joules. But then we know that the power, we said the work done by the tension divided by the delta T. So 9628,486 divided by the 2 minutes times 60. Okay, so this divided by the 120, I'm getting 80,237. Do we have to round it off? Nope. Okay, calculate the average power. So 2 decimal places. So 80,24 watts. Okay, so that is how we would have gone about that. Then we have 5.3. Will the work done by the motor increase, decrease, or remain the same if the crate is lowered, the same slope, at the same initial and final velocities? Now, what we need to know, or what we need to understand, is that if now the crate is being lowered, okay, it's like it's being given some bit of a push. So the FG parallel will be acting downwards, okay? Frictional force will be up, and then the tension will also be up, which is the tension force up this side. Okay, so those are the only forces that will be acting. Now we can see that the bigger forces are now on the opposite end. And then we only have this FG parallel on the bottom end. So according to the scenario, will the work done by the motor increase or decrease? Now, since the FG parallel is going to help drag the crate, so it's going to decrease. Okay, so if the initial is a 0 and the final is 7,5, we can look at the net work done by each of these. So remember what we say, that the FG parallel, or the work done by the FG parallel, was what? 7,454. Okay, that is now downwards. Then when you look at this, if you have to look, let's say, for the tension, which means we're going to subtract 7,494, we are subtracting the 16. Okay, subtracting 1687,5. Instead of us plusing, now we are subtracting. So meaning that the tension is going to be smaller. So 7,454 minus 1687,5 is going to be 5766,5. So we can see that the work done by the tension is going to be smaller compared to the 9,000 that was initially being done. So that would be our explanation. Can put it in words, no problem. We move on to question number 6. Doppler is now getting sophisticated. So a group of learners conducted an experiment to determine how the speed of sound source moving towards a stationary observer affects the apparent frequency of the sound that is heard by the observer. Results of the experiment are shown below. Okay, so we have this graph of ours. Then they want us to state Doppler effect in words. So we know that Doppler effect is the apparent change. Okay, apparent change in the frequency observed by the listener, or the apparent change, the frequency observed and of the listener and the sound source. Okay, so observed by the listener due to the change in the velocities of the source and the listener relative to the medium of propagation. So anything within those lines, okay, for as long as you tell us the apparent change in the observed frequency, then the change in velocities of the source and the listener, and then relative to the medium, okay, of propagation. Then write down the investigative question for this particular experiment. So since we are comparing, okay, the speed and the apparent frequency, the question should be, how does the speed, okay, I'll say, how does the speed of sound, how does the speed of the sound source affect the apparent frequency? Affect the apparent frequency heard by the observer. That is heard by the observer. And then 6.3, use the graph to determine the true frequency of the source. So true frequency of the source is that frequency when the object is not moving. Okay, when the source is not moving. So the intercept is at 150, 60, 70. It's probably 180. So I'll take it to be 180 hertz. Then use the results of the experiment conducted at a source of 100 meters per second to calculate the speed of sound in air on the day the experiment was conducted. So when I look at 100, the reading at 100 is 250 hertz. Okay. So we have 250 hertz. Okay, and then the source we said is producing 180. So this is the frequency of the source. This is the frequency of the listener, the apparent frequency. So we know that from Doppler, frequency of the listener should be V plus minus VL, V plus minus VS times the frequency of the source. Now, since the observer is stationary, and we can see that this frequency keeps going up and up and up, meaning that the source is approaching the observer. Okay, so we could say if we have our frequency of the listener, which is 250, is equivalent to V that we don't know, plus the frequency of the listener, which is 0, over V minus the velocity of the listener, of the source, sorry, is 100, multiplied by the frequency of the source, which is 180. And then all we have to do the cross multiplication. So 250 into V minus 100 is equivalent to 180 V. Open this up, we have 250 V minus, that will be a 25,000 is equal to 180 V. Let's collect the like terms, okay? So 250 V minus 180 V is equal to 25,000. Then 250 minus 180, I'm getting a 70 V is equal to 25,000, then divide both sides by 70. Okay, so when I divide that, 25,000 divided by 70, I'm getting 357,14. That is meters per second. So it's around about 340, which is the usual 330, 340, which is fine. 6.5, consider the graphs below. Which of the following graph best represents the wave as the source approaches the listener? So we know that for the source to approach the listener, the wavelengths need to be shorter so that the frequency is higher. Okay. When you look at A, we're seeing something that is symmetric or uniformly distributed, which is out. When you look at B, it starts with shorter wavelength and the wavelength increases, which means the frequency is low, it's moving away. And then option C would be the best. Okay. What would be the explanation? We can say that as the source, okay, as the source approaches the listener or the observer, the wavefronts must compress, okay, meaning that they are decreasing wavelengths, okay, thus increasing the frequency. Okay, so something of the sort. Question number 7. Two identical charges, Q1 and Q2, are placed on insulated stands, 6 millimeters apart as shown in the diagram. Okay. The magnitude of the electrostatic force that Q1 exerts on Q2 is 3 times 10 to the negative 3. Point X is at a distance D to the right of Q2. State Coulomb's law inwards. So Coulomb's law simply tells us that the magnitude of the electrostatic force that is between 2 point charges or between two charges is directly proportional, okay, directly proportional to the product of the charges, the product of the magnitude of the charges, and inversely proportional to the square of the distance that is between them. All right, so something of the sort. Then 7.2, telling us that a learner has decided to draw the electric field pattern between Q1 and Q2. State whether the learner has drawn an electric field pattern for 2 positive or 2 negative. Now we know that if the charge is positive, the field lines should be moving away. If it's negative, the field lines should be entering. When we look at our drawings, the field lines seem to be entering, okay? So these are negative charges. Okay, so it's 2 negative charges. So they want us to give 2 reasons. So the first reason, we shall say that the field lines, they just point inwardly or inwards, or they just point towards, inwardly to the sphere or towards the sphere. And then number 2, we could say that the field lines, they bend away from each other. The fact that they are bending away from each other simply means that they are negative or they are of the same charge. Then 7.2, they want us to get the magnitude of Q1. Okay, so we have the force. Okay, so what we're going to do, we're going to say that the force, electrostatic force, is given as K Q1 Q2 over R squared. The force we're given was 3 times 10 to the negative 3 is equal to 9 times 10 to the 9. Q1, Q2, same thing, so I'll say it's a Q squared over the distance, which is 6 over 1,000, 0.006. We square that. Okay, so we can do the cross multiplication once and for all. Okay, divided by 9 times 10 to the negative 9 is equal to Q. We can put this under square root so that we get just the charge for one of the spheres. Okay, so when I punch everything into my calculator, I'm ending up with a 3.46 times 10 to the negative 9 coulombs. Okay, so that is the charge on Q1 or Q2, either way. Then 7.4, they're telling us that the electric field due to Q1 only is 3.33 times 10 to the 5 to the left. Calculate the magnitude of the distance. So we're seeing that Q1 has this distance of 6 plus a D. Okay. So I'll come down and say that our electric field strength will be given as KQ over R squared. Okay. So our E that we're given was 3.33 times 10 to the 5. That's 9 times 10 to the 9. We found the charge to be 3.47. Is it 47 or 46? We found 46. times 10 to the negative 9. We're dividing this by the r squared. So let me start by finding the distance between P.1 as well as the point. Then I'll bring in the 6 plus d at the end. So meaning that our r squared is going to be 9 times 10 to the 9 multiplied by 3,46 times 10 to the negative 9 divided by 3,33 times 10 to the 5. Okay, so when I punch this into the calculator, I'm getting, that's times 10 to the 5. Oh, I'm getting a very, very big answer. Okay, then I need to find, okay, I'm getting 0,0040935. Then I need to find the square root of that. Okay, so if I find the square root, I'm getting 0,0967. This is meters, né? So when we change this to millimeters, this should be 9,67 millimeters. So we know that 6 plus d should give us a 9,67 millimeters. Then let's find the difference, okay, whereby d is going to be a 9,67 minus 6, which gives us a 3,67 millimeters. All right, so that is question number 7. Question number 8. In the circuit below, the battery has an EMF of just 12 volts. The internal resistance is R. The 3 resistors and the light bulb are connected as shown. The resistance of the bulb is 2 ohms. Initially, S1 and S2 are open. Connecting wires have negligible resistance. Then they want us to define the term EMF. So EMF simply represents the work done by the battery, okay, to move an electron charge around or electric charge around the circuit. So we can say that the work done, okay, per unit charge by a battery to move the electric charges, around the circuit. All right, so with only S1 closed, okay, if that is closed, the reading on the voltmeter drops. So meaning that our V external is 10,8. Okay, so let's see. Okay, so they want us to get the reading on the ammeter when S1 is closed. So what we can see is that if S1 is closed, then current will be passing through the 6 and passing through the 6. The 3 and the 2 will be out since there is no way current will go there. So we have our V external as the 10,8. Okay. So we don't have the internal resistance. Only thing we can do is use Ohm's law to say V is equal to IR. We have the voltage, which is the external voltage, okay, which is 10,8. And then we need to get the effective resistance. So effective resistance is going to be 6 and 6. Since they are in series, I'm just going to add them together, okay? So meaning that our resistance is going to be a 6 plus 6, which is 12 ohms. And then from V is equal to IR, we need the current, which is going to be the V external, which is the 10,8 divided by the 12. Okay, so this gives me a 0,9 amps. Okay, so that is the total current that we are having. A lot, you know, it's small current that is flowing. Then they want us to get the internal resistance R of the battery. Okay, so since we know that the EMF is 12, the V external is 10,8. We can get the V internal that represents the lost volts, which is 12 minus 10,8. Okay, so 12 minus 10,8 gives me 1,2 volts, meaning that my V internal is given as I times small r. Then we shall have a 1,2 is equal to the current that we have as 0,9 multiplied by R. So over 0,9 over 0,9, and then my R becomes 1,2 divided by 0,9. We have 1,3333, which is the same as 4,3 ohms, or 1,33 ohms. Okay, so that is our internal resistance that the question wanted, 8.2.2. All right, then 8.3. The scenario kind of changes. Now they are saying that both switches are closed and the ammeter reading is now 1,5. So initially it was a 0,9. So when you connect this, you're producing some sort of a parallel combination. And with the parallel combination involved, the effective resistance must reduce, meaning that more current must flow. Okay. So if more current is flowing, because where's the ammeter? Ammeter is here, meaning that the total current flowing is 1,5. So if it's 1,5, we can find the power dissipated by the bulb for 7 marks. Yo. Okay, so I'll start by getting the effective resistance within this parallel combination, okay? So because that will be like a 6 on top, okay, this 6 here, and then 3 plus 2 is gonna be a 5. Okay, so if these two are in parallel, we know that let me just put it aside and say that the effective resistance of the parallel is gonna be the product over the sum, which product is gonna be 6 times 5 over 6 plus 5. Okay, when I punch that into the calculator, I'm getting 2,727, which is 73 ohms. Okay, so this is the effective resistance for just a parallel combination. Now, do I need to get the voltage? Yes, I can get the voltage that is across here, because the voltage here and the voltage here must give us the total voltage across. So what's going to happen is that I'll get the voltage across the parallel, which is current multiplied by the effective resistance. So if the current is 1,5, the effective resistance is 2,73. What we get? 1,5 multiplied by 2,73. That gives me a 4,095 volts. Okay, so if this is a 4,095, okay, just across the parallel, we know that the voltage across the parallel must be the same. Okay, so if I look at the 6 ohm here with the voltage, I can find the current that is flowing through this bulb, because the current is going to pass via this 3 ohm up to the bulb. So let's get the current through the 6 ohm. So current of the 6 ohm of the parallel, we know that V is equal to IR. So it's going to be V over R. So 4,095, I'm dividing it by 6. 4 divided, no, it's 4,095 divided by 6. It gives me a 0,68 amps. Then the current through the 2 ohm or through the bulb will be 1,5 minus the 0,68. Okay, 1,5 minus the 0,68, which gives me the 0.81 amps. Now, why is it a 0.81? Because we see that the total of this 3 and the 2 is smaller compared to the 6. So less current will flow up and then more current will flow down. Now, since I have my current, okay, as 0.8, and then I also have my resistance as a 2, the question wants the power dissipated by the bulb. Okay, so let's see. We know that from the formulas of power, we can have IV, which could also translate to I squared multiplied by R. So I'm going to use this. Mean that it's 0.81 squared multiplied by 2. Guys, please, if you worked out this separately or differently, just give us the approach you used to get the 7 marks. So this gives me 1.31 watts. Is it reasonable? Maybe, but that's what I'm getting. 0.81 squared multiplied by the current, which is it's 0, multiplied by the resistance, which is 2. That's what I end up with. I don't know what people got with that regard. Okay, so there could be other ways whereby you look for you have the current and then you look for the voltage and then, but I feel that is what I would have done. Then 8.3.2. What effect will the closing of both switches have on the internal volts or the lost volts? Now, what's going to happen is that since the overall resistance decreases, the total current will increase. And we know that the lost volts will be the V internal, which is IR. If the current increases, even the lost volts must increase. So number one, we're choosing increase. What is the reason? We're saying closing both switches brings about a parallel combination, which reduces the external resistance. Okay, and if external resistance is decreased, thus increasing the current. It increases the current, and we know that current is directly proportional to the internal volts. Okay, that's the increase. Okay, so that is how we would have answered question number 8. Question number 9. The simplified sketch below represents the structure of a motor of a cordless drill. Okay. Name the electrical component in the above motor that ensures that the coil rotates in one direction. So that's what we call the split ring commutator, or some people call it the armature. All right, then identify the polarity of the magnets A and B if the current flows in the coil. So we need to use the right-hand rule. And then if I apply it here, okay, right-hand rule, seeing the current is in that direction, so meaning that my force is in that direction as well. So meaning that A represents the north and then B represents the south. So it's saying A is the north and then B is the south. And then 9.2, the maximum current output of another drill operating on AC current is 10.6 amps. The graph represents the potential difference of the drill against that. Okay, can you define RMS current? So we know that RMS current is more like a steady, okay, unequivalent DC current that would deliver, okay, that would deliver just the same amount of power or the same average power to a circuit as the AC current, as the AC or as the maximum AC current. Then calculate the RMS current. So we know that I RMS is given as I max divided by the square root of 2. So 10,6 divided by square root of 2. That gives me 7,5 amps. Okay, then hence calculate the average power. From our formula page, we know that average power is given as VRMS multiplied by RIRMS. So we have the potential difference, and we know that the maximum is 300. So we're going to have 300 over square root of 2 multiplied by what we just got, the 7,5. I punch this into my calculator. I'm getting 1590 watts. Okay. Or someone could say 1,59 kilowatts. Okay, so that is 9.2.3. And the 9.3.4 is the power generated by the drill at T1, maximum or minimum. So we're seeing here at T1, that's when we have the maximum potential difference. And we know from the formula of power, we have IV, okay? So voltage is directly proportional to the power. So that power is maximum. Okay, the 9.2.4, 2 reasons why we prefer alternating current over direct current. So direct current is basically current that can be stored in batteries, and AC current can hardly be stored. So reason as to why we choose the AC is that it can easily be stepped up, okay, using transformers to high voltages. Okay, number 2, it can be easily be transported or transferred or transmitted over long distances. So the electricity that is over the cables is mainly the AC before it gets to the transformers. Okay, question number 10, learners demonstrate the photoelectric effect of irradiating the green and then the blue light on the photocell as shown below. A reading is registered on the ammeter when the green light is used on the photocell. Provide a reason. Okay, so the reason we must give, or we can give, is that the frequency, okay, so frequency of the green light is greater than the threshold, is greater than the threshold frequency of the metal in the photocell. Okay, then 10.2, the green light is now replaced with a blue light of the same intensity. Okay, and irradiated onto the photocell. What influence will this have on the following? Number 1, the kinetic energy of the photoelectrons. Are they going to increase, decrease, or stay the same? So in this case, kinetic energy will increase. The reason being is that blue has a higher frequency. Blue as a light has a higher frequency than green. Okay, so higher frequency means more energy. Okay, and then what about because we're saying the green light is now replaced with blue with the same intensity. How will the ammeter reading be affected? Increase, decrease, or stay the same? So the ammeter reading is going to stay the same. Why? Because the intensity is the same, and the ammeter reading is basically taking the readings of the intensity. So the reason is going to be intensity does not affect the frequency. Intensity does not affect the frequency, and we are saying that it is EK that depends on the frequency. Okay, so intensity, but even this last statement doesn't make sense. We can just say that the same intensity is not affected by the change in the frequency. All right, then The wavelength of the blue light is used in the demonstration is having this wavelength for the blue light. Calculate the cutoff frequency or the threshold F0 of the metal used if the photocell has an average speed of this much. So what we can do in this case is that we know that the energy, let me just put it aside, energy will be W0 plus the EK max. Okay, so this is Planck's constant and the frequency. This is gonna be Planck's constant and F0 is equal to 1/2 mv squared. Now, we were given the wavelength. We need to change that. We know that C is equal to F lambda. And frequency is going to be C over lambda. So 3 times 10 to the 8 over the lambda, which we were given as 4,5 times 10 to the negative 7. Okay, so when we punch this into our calculator, 3 times 10 to the 8, we're dividing it by 4,5 times 10 to the negative 7. I'm getting a whole lot of 6s. That's 3, 6, 9, 12, 15. Okay, so this is our frequency, meaning that if we do our substitutions here, it's going to be 6,6 Planck's constant, 6,63 times 10 to the negative 34. I'm multiplying it by 6,67 times 10 to the 15 is equivalent to my Planck's constant, which is 6,63 times 10 to the negative 34, F0, plus 1/2 times what is the mass of the electrons, 9,11 times 10 to the negative 31. We were given the velocity of 4, what was that velocity? It's 4,62. Okay, so 4,62 times 10 to the 5, this is squared. Okay, so simplify the left-hand side. Simplify the left-hand side, I'm going to end up with 4,42 times 10 to the negative 18. Now I need to move this to that other side, which will be a subtraction. I have 9,638 times 10 to the negative 20 is equal to 6,63 times 10 to the negative 34, F0. Okay, so I'll do my subtractions. And then what do we get? Let me just, okay, that is times 10. We're multiplying times 10 to the 15. This is a 4,42. Perfect. So when I divide by 6,63 times 10 to the negative 34, same story, 6,63 times 10 to the negative 34. Okay, so my F0 that I'm ending up with is a 6,52 times 10 to the 15 hertz. Okay, 6,52. Okay, so that is what we are getting. This was a 6,67, which emitted. Okay, makes sense. Okay, so that is how I would have gone about with that paper. Please remember, this is just the proposed memorandum. The memorandum is not yet out. I wish you guys all the best in your remaining papers. I sign out. Hello, welcome to this episode where we shall be looking at the proposed memorandum for the Physical Sciences Paper 1 for September 2025. Okay, so this paper is a 3-hour paper with 150 marks. We have 16 pages and we have a total of 10 questions that we have to work with, and we need to answer all of them. Okay. Let's start with the MCQ, which is question number 1. And they're telling us that a mass hangs